Welcome to Module 4 of the SUST 3D Fashion MOOC, Introduction to 3D Printing Technologies. This course explores how 3D printing transforms fashion, from materials and methods to sustainability and innovation. 3D printing, also called additive manufacturing, builds objects layer by layer. Unlike traditional methods, which cut away material, this technology adds only what is needed, reducing waste and enabling complex forms. This distinction matters. Subtractive manufacturing is resource-heavy, while additive manufacturing saves material and energy. In fashion, that means fewer scraps, lighter footprints, and new creative opportunities. Module 4 focuses on technologies that make this possible. We'll see how materials, machines, and processes combine to create new tools for sustainable and innovative fashion. Let's begin with filaments, the raw materials. Choices include plastics, bio-based materials, and composites. Each has unique properties affecting durability, flexibility, and sustainability. One example is PLA, a biodegradable plastic derived from cornstarch. It's popular for prototypes and educational projects because it's safe, affordable, and eco-friendly. Another is ABS, a strong petroleum-based plastic. It's durable but less sustainable. Designers often choose ABS when strength and heat resistance are priorities. Beyond plastics, innovation brings new biomaterials. For instance, Laywood and Grow Lay mix polymers with wood or organic fibers. They create natural textures and can even be composted. Biomaterials bridge sustainability and creativity. They show how fashion can move away from synthetic waste toward materials integrated with nature. 3D printing technologies vary widely. Let's explore the three main categories most relevant to fashion: FDM, SLA, and SLS. FDM, or fused deposition modeling, is the most common. It melts and extrudes filament through a nozzle, building parts layer by layer. FDM is cost-effective and accessible. Small studios, schools, and even homes use it. It's perfect for prototypes, accessories, and experimental pieces. However, FDM has several limitations. Its surfaces often show visible layer lines, finishes are rough compared to resin technologies, and the accuracy of small or intricate details is lower. Extra post-processing is usually required. SLA, or stereolithography, works by curing liquid photopolymer resin with a precise beam of light. This process builds parts layer by layer, achieving very fine features and smooth surfaces suitable for premium applications. SLA is valued for its ability to create smooth, high-quality parts with crisp details. Designers can experiment with delicate geometries that are nearly impossible to sculpt by hand, while maintaining a luxury-grade aesthetic. Still, SLA has drawbacks. It involves handling liquid resins, requires washing and post-curing, and relies on support structures that must be removed. Costs are higher, and materials can be brittle, limiting everyday accessibility. SLS, or selective laser sintering, uses powerful lasers to fuse fine polymer powder into solid forms. Because the surrounding powder supports the part, even complex shapes and interlocking structures can be produced without supports. In the fashion sector, SLS is especially useful. It enables durable lattice midsoles, lightweight accessories, and prototypes that combine flexibility with strength. These qualities make it ideal for wearable, functional designs. The trade-offs of SLS are clear. Machines and powder systems are expensive, finishes are grainy without post-processing, and maintenance is complex. Yet its ability to deliver strong, reliable, and intricate parts is unmatched. Let us now move to case studies. Real examples show how different technologies come alive in practice, proving their creative and sustainable applications within fashion, healthcare, and consumer design. In Germany, Laywood and Grow Lay filaments demonstrate how eco-materials reshape design. Laywood mimics natural wood aesthetics, while GrowLay even supports biological growth on the surface, opening paths for eco-fashion. Another example comes from the USA. Medical centers use PLA to print biodegradable anatomical models. These replicas reduce costs, accelerate training, and minimize plastic waste, showing sustainability in healthcare. Berlin's VOJD studios apply SLA technology to create luxury jewelry and accessories. By combining high-resolution prints with traditional finishing, they deliver pieces that meet the standards of top fashion houses. Hamburg's Zellerfeld redefines footwear with fully 3D printed sneakers. Each pair is printed on demand from one recyclable material, reducing waste, enabling mass customization, and reshaping the global supply chain. These cases show how each technology answers different goals: SLA for detail and refinement, SLS for strength and complexity, or bio-based filaments for sustainability and creative storytelling. Choosing a technology is never just a technical matter. It is about aligning tools with the designer's goals, sustainability priorities, available resources, and the expectations of the final consumer. Beyond the printer itself, the entire workflow shapes results. Scanning, digital modeling, slicing, and post-processing all influence quality, cost, timing, and even environmental footprint. Take slicing, for example. Settings such as infill pattern, density, layer height, and orientation decide not only how strong or efficient the part will be, but also how much material and energy it consumes. Post-processing plays a critical role. Sanding, coating, dyeing, or assembling can transform a raw print into a polished, professional product. Luxury brands invest heavily in these finishing steps to ensure value. Sustainability must remain central. Designers are asked to choose circular materials, localize production, minimize waste, and plan for repair, reuse, or recycling. 3D printing supports this shift when applied consciously. Challenges still exist: high energy consumption, difficulties in recycling certain materials, and gaps in technical skills. Overcoming these requires training, innovation, and stronger industrial collaboration. In vocational training, learning these technologies develops creative confidence and technical competence. Students acquire sustainable mindsets and practical skills that are vital for tomorrow's fashion industry. Now, it's your turn. Think about which technology best fits your project, which material supports your sustainability goals, and how your design decisions reflect a balance of creativity, cost, and responsibility. Experimentation is highly encouraged. Even a simple object, such as a buckle, button, or clasp, can teach valuable lessons about design tolerances, workflow choices, and finishing techniques. Reflection is key. Consider what you gained in creativity, comfort, or function, and what you compromised in cost, time, or finishing. This critical analysis is as important as the printed object itself. To conclude, Module 4 explored the core 3D printing technologies. From FDM's limitations to SLA's precision and SLS's strength, each offers unique opportunities for sustainable fashion innovation. Thank you for following Module 4 of the SUST 3 Fashion MOOC. With this foundation, you are ready to apply what you learned, explore new projects, and continue the journey with Module 5.